Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of chest X-ray images in which we have three cases: normal X-ray, bacterial pneumonia, or viral pneumonia. Now, the bacterial pneumonia and viral pneumonia have been combined together into just a single pneumonia folder. But essentially what we have in the train set is a bunch of images of normal chest x-rays. I'm not sure, we can't actually see them right now. But we also have ones with pneumonia. So as you can guess, the idea here is let's try to predict whether a given image whether pneumonia is present or not. And we're going to do this using a pre-trained TensorFlow CNN. What I mean is there are these models that have been trained for hours, maybe days, with enormous data sets, such as the ImageNet dataset, which predicts. So these models were used to predict up to, in the case of ImageNet, is 1,000 different classes of image. And what you do is take one of those models and which is very generally good at understanding images, and you narrow down its applicability to fit your need. So you train on top of a pre-trained model. And in this case, we're going to be using MobileNet v2, which is sort of a lightweight version of some of these more heavy transfer learning models. So let's get into it. I have NumPy. Actually, we don't need pandas today. But we're going to use NumPy, matplotlib.pyplot, and Seaborn for visualization. And we're also going to get the confusion matrix from sklearn.metrics. Then TensorFlow we'll use for building the model. So I'll go ahead and import those, and let's start by just getting our paths to our folders. So by default, one of the most standard ways to organize the images is put them in folders based on classes. So the class names are going to be inferred by the folder they're in. So if we just get these directory names, so I'll call it traindir, is going to be just the link to this. I can copy the file path, but Kaggle is an issue there. I just have to type in /chestxray/train. That's the path to the train folder. Okay, then I'm going to do it again for the validation folder. I'm just going to change this to val, or both of these to val, and then I'm going to change this one to test. So now we have a train directory, val directory, and test directory. Then I'm just going to initialize some constants, the height of an image. So this is what we're going to rescale the images to. We're going to make them 224 by 224 pixels. And 224 was what the MobileNet architecture was originally trained on, so it just makes sense to me to keep it that way. And we'll set up a batch size of 32. Alright, now I'm going to set up some data generators. And what this is going to do is it's going to basically allow us to take images from the folders and feed it into our environment here, so that it's nicely represented as an array of pixel values. So we can get these data generators, and we'll call this train data gen, is going to be tf.keras.preprocessing.image data generator. And we can now specify some arguments that we want, like transformations we want to apply to the image. The first one, which we're going to use on all three of our generators, is going to be rescale the image by a factor of 1/255. So that means let's take all the pixel values, which are RGB values from 0 to 255, and let's squash that range down to between 0 and 1. Just makes it simpler for our model and improves performance. So here's our train generator, and I'm going to do also one for the validation set and also one for the test set. Now these are identical, But for the train generator, I also want to include some image augmentation arguments. And so what this will allow us to do is generate new data, new images, from the images we already have. And this can have tremendous improvements on performance. It takes longer training time to do this, but it's usually worth it. So for example, we can rotate the image by specifying a rotation range, 20 degrees. We can change the image's brightness. Brightness range is, this takes a tuple of a range of values 1.2 to 1.5 sounds good. And we could, how about we do horizontal flip? Generally you want to apply transformations that are realistic to see in the data set. For example, we wouldn't want to like swirl the image, because that you would never see an X-ray that looked like that. But for example, a flipped X-ray is very similar to what an actual X-ray would look like, what an actual piece of data that this model would take in. So it's these seem good to me. And then, once we have those data generators, we're going to feed in the data using the datagen's method called flow from directory. And this takes in a path to image files, and we don't even have to worry about the classes. It'll automatically get those based on the names of the folders. All we have to do is give it the link, which is traindir. Write this one up here. Then we also want to specify a target size. This will be the size of an image, image height by image width. We also want to specify a class mode. Because we only have two classes, we're going to specify its binary, and we'll feed in the batch size. Alright, now I'm going to flow from directory and then store it in train data. And we can do the same thing for the validation generator and the test generator. So this will be valdata and valdir, and this will be test data and testdir. Alright, and if we flow now, we'll get, you can see, found 5,216 images belonging to two classes, 16 images belonging to two classes, and 624 images belonging to two classes. So this is train, validation, and test. Alright, and now we will create our pre-trained model. So I guess I should probably just mark this down a little. I'll say getting started here, then creating data generators, and now building the model. So we're going to create this MobileNet model, and we're going to load this in from one of Keris's pre-trained models using tf.keris.applications.mobilenet-v2. And this takes a few parameters, a few arguments. An input shape, which will just be image height by image width by 3. And 3 specifies two color channels. Now, these are black and white images. However, the original MobileNet model was trained with 3 color channels. So I think that there actually is a way to make it black and white. Let me look this up real quick. MobileNet v2 and Keris. Okay, we'll do this. This is what we're using, right? Alpha. No. Yeah, I'm not sure if there is. It says that it should have exactly 3 input channels. Huh. Yeah, so I believe other models allow for this though. ResNet? Maybe not. Okay, I'm not going to go too far into this. But it was originally trained with 3 color channels, so we'll keep 3 color channels on there. And we're also going to say include top equals false. And what this means is at the end of the MobileNet architecture, it was, like I said, trained to classify 1,000 different classes of image. And so at the end, it has a dense layer with 1,000 nodes, 1,000 activations. We want to take that off because we want it now to build on top of this pre-trained model. So we're saying include top false to not include that final dense layer that spits out classification predictions. Now for weights, we want ImageNet, and this is saying, one second. For weights, we want to use the weights that it was originally trained with on the ImageNet dataset. The last thing we'll specify is pooling average, and this will just put on an average pooling layer at the end of the dataset, which will allow us to have one vector output. Alright, so we'll load that in. Should just take a second. We can start training our model. We'll build a model. So epochs, we're going to train for 50 epochs, and that's a lot, but it's okay because we're going to use the early stopping callback. And then we'll create an input layer, tf.keras.input. Shape will be image height by image width by 3. Alright, our pre-trained model will come next. This is just going to be the mobile net that we just defined up here, and we're going to pass in inputs. Then we'll have a dense layer after tf.keras.layers.dense, and this is going to take this is going to have 1024 activations with a ReLU activation function, and we're going to feed in the outputs from pre-trained model. Alright, and then our final output layer is going to be another dense layer with one activation. This will be a sigmoid activation that will represent the probability value of the estimate of whether a given image has pneumonia or not. And we pass in dense to that, and now we can create our model. Model equals tf.keras.model. Pass in inputs and outputs. And then we can compile it. Maybe we should get a summary first. We can see most of the parameters we're going to train are here. However, we are using, we don't actually want to train them. We want to keep them the way they are. So what we'll do is up here, we'll say mobilenet dot trainable equals false, and that will keep the weights from being trained. We should also over here specify training equals false. So now you'll see we still have the parameters there, but it says non-trainable params, and that's just these ones. So we're only training parameters here and here, the weights between these three layers. And so we'll finally get that output. I'm now going to compile and run the model. Model.compile. We'll use an atom optimizer. And for loss will be binary cross entropy. And our metrics, because we have two classes, we'll use accuracy, and I also want to use AUC here. So tf.keras.metrics.auc. Give it a name as well. Okay, and then once we've compiled it, we specified a number of epochs up here, but I think it's probably better to do that down here. We'll store our model's training history in history. So model.fit, and we're training on trained data. We also want to specify validation data, which will be val data. These were flowed from the directories earlier. Then we'll specify batch size and epochs. And we'll include that callback function I was talking about. So this is tf.keras.callbacks.early stopping. And basically, this lets us monitor a value, in this case the validation loss. And when we notice that it starts to go back up, when it starts to overfit for a period of 3 epochs or longer, that's what patience is, then we're going to stop the training and restore the best, the weights from the best epoch. So I'm putting restore best weights on as well. Alright, let's train. Now let's see how this goes. Now, this is, I have enabled GPU acceleration, but even with that, this will take a while. So I will pause the video and come back when we have finished. Alright, that took about 20 minutes or so. And you can see our model trained for 6 epochs before stopping. That is because the validation loss started increasing. And you can see it will have restored the best epoch, the weights from the best epoch, which looks like this one, where we had a validation accuracy of 87.5%. Now notice this value here is not so indicative because we only have 16 images in the validation set. Right up here it says 16 images. So let's see how it does on the test set, which has 624 images. So results. I'm going to, before I check it right away, I'm going to create 2 arrays. One will be true labels, and this is just going to be test data.labels. So right here, test data.labels is just the labels associated with all the images in the test set. So I'm going to call that true labels, and then the predicted labels is going to be what our model predicted. So model.predict test data. So this is going to be our predictions. Now if I look at that, model.predict test data is going to be probability values. So values between 0 and 1, which doesn't exactly match up to the labels in true labels. However, the way we classify, so here you can see the probability values for each example. How basically this is, if it's over 50%, it means it has pneumonia, or we think it does, and if it's under 50%, it means we don't. So what we'll do is we'll say greater than or equal to 0.5, and this will return a Boolean array, right? Because it's just each one of these will become a true or false value, depending on if it's greater than 0.5. And what we'll do is turn that into a new NumPy array, but specify dtype equals numpy.int, and that will give us, it'll change the Boolean values of true false into 1 and 0, which will give us the labels just like this. And then the last thing to do after that is we want to squeeze out the dimension. There's an extra dimension in here. Sorry, it should be squeeze. So you see how this is actually a list of lists, right? There's these little lists in here that will squeeze out that extra dimension and just make it one long array, just like true labels. And that will just have these both have the same shape. Now I'm going to create a confusion matrix, and this I got from sklearn. Confusion matrix of true labels and predicted labels. Alright, now I want to plot the confusion matrix using Seaborn. plt.figure creates a new matplotlib figure. Specify fig size of, but we'll do 6 by 5. We'll do 6 by 6. And sns.heatmap, seaborn.heatmap, we'll create a heat map of CM, which is our confusion matrix. We want to turn on annotations. Let's format the annotation values so that we just see the integer values and not in scientific notation. And then I want the minimum value to be 0, which would correspond to no examples in a given category, and also give it a nice color map. One more thing before I do this, I want to look this up. I want to see if there's a way to take off that thing on the side. Whether to draw a color bar. I think Yeah, I think that's it. C bar equals false will do. C bar equals false. And then plt.show. Here it is. So this is true positives. This is true negatives. This is false positives and false negatives. Wait, no. Which one is the... This is false positives. And this is false negatives. And you can see we have a lot of false negatives. So let's see how this did. Going to evaluate the model and store it in results. So we're going to evaluate on the test data, and I'm going to set verbose equals 0. And I'm going to store the results in accuracy, which will just be results sub 1, and AUC, which will be results sub 2. Then I'm going to get the true negatives, false negatives, and true positives from the confusion matrix .ravel. And this is a NumPy function that will just take a matrix and convert it into a single array of values, which will then save like this. Precision is the formula for precision is true positives over true positives plus false positives. So essentially, precision is based on all everything we predicted positive. How many of those were actually correct predictions? And recall is going to be true positives over true positives plus false negatives. So recall is out of all the ones that are actually positive, right, which consists of true positives or false negatives, which were actually positive. How many of them did we classify correctly? And these are some good ways of getting an understanding about the data, especially when we have imbalanced classes. Now, I'd like to print out all of these. So accuracy, and I'm going to format the strings here. So :.2f to get 2 decimal places, .format accuracy, right? And then I'll do one for AUC, precision, and recall. UC, AUC, precision, and recall, Alright, and here we are. So we had an 80% accuracy, 0.94 AUC, precision of 0.64, and recall of 0.79. So this is okay. It's not exceptional. I'm sure we could do a better job. We ended up getting quite a few false negatives here. I should really label these, but you see, it seems like we classify a good number of true negatives, but not nearly as good in the positive class for true positives. This is very misleading. I have to change the ticks here because it looks like this is the negative class, but it's really not. So we just do this. How about normal? Wait, no. Actually, give me one sec. Okay, sorry. I was just looking up how to get this this thing. We use class indices to find a mapping between the original class name and the number. So because we know 0 is actually normal, I'm going to write normal here, and pneumonia here. And I'll do the same thing for the y-ticks. Oh, I did it wrong. How do we do the ticks? Hold on. X-ticks, not MATLAB, matplotlib. So plt.xticks takes a list of ticks, locations, and then labels. Okay, so I need a range. So this is just the names. We also need a range of 2. Okay. Close enough, right? Come on, there has to be something better. How do we get it in the middle? Oh, hold on. Can I do plus 0.5? Yeah, that did not work. Oh man, see, because it's doing 0 and 1 directly on the corner. Yeah, let me get it right. Okay, I did a little, just quickly look this up. Apparently, we can use numpy.arange to do exactly the same thing, but here we can actually add 0.5, so I did have the right approach. numpy.arange plus 0.5. This should set the text to be right in the center, and I'm also going to include the font size to make it a little nicer. Alright, so, right, so this is normal and normal. I should really, just give me a sec. Plot.xLabel is going to be, so on the x, this is the predicted value, and the y label, plt.ylabel, is going to be the actual value. Okay, so this is predicted, this is actual. Now we can see true positives properly. So we predicted this with pneumonia, but is actually normal. So this would be, well, it depends on what you mean by positive. In any case, we got the results, we got our confusion matrix. I think it was pretty successful. Pretty decent accuracy, pretty decent AUC, pretty decent precision, pretty decent recall. I think someone, I was looking at another notebook, and they got really good results by, instead of using a full pre-trained model, they created their own model and then took the weights from a pre-trained model and only used them in the first couple layers of their model, which gave them better results. So I'll definitely consider doing that in the future. But this is supposed to just be like a simple tutorial on image classification. So I hope you enjoyed the video. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.